Hi, my name is Zhao Zheng.
And I'm Alexander Ortiz, and this is our Thermodynamics Project 2, Vapor-Liquid Equilibrium Behavior, Predicted Model, and the Isothermal Experiment data. So the overview project: create a data set for C and D that represents the liquid and vapor fraction experimental pressures and the calculation of activity coefficient, log activity coefficient, and liquid vapor fraction squared for two components for data C and D. Then construct a chart that represents the vapor fraction versus the liquid fraction of component 1 to show the vapor-liquid equilibrium behavior. With that being said, if one of the data sets fails to follow Rolle's law behavior, then we will determine the best activity coefficient by using the different models, such as Margulis single parameter or two parameter model, or Margulis or Banlard and Wilson's equation.
We need to create the table 1 and 2 for given data sets of C and D at particular temperature of 303.15 kelvins, and the data where the molar fraction of liquid phase is equal to the vapor phase. Then, with the information rearranged, we proceed to graph adjust our pressure again. S1 equal to Y1, as shown in two graphs above. The graph from the left corner, we could see the linear line trends fits well with the liquid fraction of component 1 as bubble curve, and with the correlation value is getting very close to 1. So the binary system of C strongly follows the Rao law. However, the graph from the right top corner, we could see the bubble curve wasn't straight line, so this system did not follow Rao law. Besides that, the blue line intersects with the red line in our Zabatrite system, meaning the vapor phase and the liquid phase of component 1 has the same boiling point and no separation will happen at this point. Secondly, we plot a graph S1 equal to Y1 to understand the VLE model, and the linear line of Y equal to X help in making the representation of behavior when compared to blue line of Y versus X, with the correspond to equilibrium value. We can say any point on the blue lines that correspond to the composition of vapor and liquids in equilibrium at a different temperature.
So for failing Rolle's law, as we have seen, science data set does not support Rolle's law behavior based on the PLE model. We must do the following models for us to determine which one will be the one best to describe the behavioral system data D. So we will be starting with Margulis single parameter model, and then we will move on to Margulis two parameter model, and then we're gonna do Banlard's equation, and then finally we will finish with Wilson's equation. So we will start with a simple model, which is once again Margulis single parameter model equation, which is shown below. First of all, we will determine the activity coefficient for the two components of gamma 1 and gamma 2 by using the equations listed below as well, which were the derivative from Margulis modified law equation, where saturated pressure for component 1 will be equals to 404.6 kilopascals, while for component 2, it will be equals to 178.1 kilopascals. Then we will calculate the mole fraction of the liquid phase squared and the logarithm of the activity coefficient to use this information to set a graph showing the linear behavior to obtain the activity coefficient, which will be the slope of the linear lines for each graph. With both graphs completed, we determine that our slope matches one another from the two Margulis single parameters, which is showing the slope on the graph, obviously. And then with this, we can determine that our coefficient will be 1.5 or activity coefficient in each single graph.
For Margulis two parameter models, the equation shows the relationship between the activity coefficient and the mole fraction of the liquid phase. For this model, we plot both gamma 1 and gamma 2 versus the mole fraction of component 1 in liquid phase, and we can see the point are good fit on the polynomial trend line, and the correction function is also close to 1. So as infinity dilution for gamma 1 is equal to 4.5, and for gamma 2 is as 4.8. So logarithm of gamma 1 is equal to parameter 1, 2, and also equal to 1.5. Follow that logarithm of activity coefficient 2 is equal to parameter 2, 1 equal to 1.56.
So we will now start with the balanced equation. For balanced equation, even though the general equation is different from the Margulis two parameters model, it's essentially the same steps to follow to obtain gamma 1 and gamma 2 for the infinite dilution, which are going to be 4.5 and 4.8 respectively. And if we use the information, we will find that delta logarithm of gamma 1 will be equals to a prime 1 to 2 with the equals to the value 1.5, and logarithm of gamma 2 for equals to a prime of 2 to 1 will be also equals to 1.6.
Now for Wilson equation. So for equation, when x1 equal to 0, x2 gonna be equal to 1. So we can rewrite the equation phi s lambda 2, 1 is equal to 1 minus logarithm of lambda 1, 2 minus logarithm of gamma 1. And follow that step, we can also rewrite lambda 1, 2 equal to 1 minus logarithm of lambda 2, 1 minus logarithm of gamma 2 as equation 6. And if we rearrange equation 5, we can get the lambda 1, 2 equal to exponential of 1 minus lambda 2, 1 minus logarithm of gamma 2 at equation 6 prime. And also we assume that lambda 2, 1 is run from 0.05 to 1. And to calculate the logarithm of gamma lambda 2, 1. And also we calculate lambda 1, 2 by using the equation 6 and 6 prime. After we got the result, we're gonna create a data table results. And from the graph, we can read the coordinate of the intercept lambda 2, 1 and lambda 1, 2 as 0.4 and 0.4.
So for a conclusion, we can use Rolle's laws to identify and understand the behavior of each system as long as they follow the Rolle's law behavior. However, as we have seen, the set data for the not support Rolle's law compared to the other data sets. For both, we can use the modified Rolle's law and different models to explain the system D compared to see which models will be more accurate.
Thank you so much for listening.
Thank you for listening.